Hello everyone and welcome to the next lecture of the NPTEL course Machine Learning for Core Engineering Disciplines. In the last lecture we learned about how mathematically one can formulate the prediction of a simple feed forward neural network with fully connected layers. A fully connected layer means that every node in each layer is connected to all the nodes in the next layer and there are no skipped connections. Now what we are going to do in today's lecture is we are going to see how the weights and biases, which are the model parameters, they can be obtained by training a neural network. So let us go ahead and get started. The topic for today is training of an artificial neural network, and we are going to discuss about a simple feed forward neural network with fully connected layers. Okay. Now before we start the training process we have to specify the hyperparameters of the neural network. So what are the hyperparameters? We already know from our discussion before that hyperparameters set the model architecture and specify the details of the training process. Okay. So in our case the hyperparameters, those which set the model architecture, these include the number of layers, the number of nodes in every layer, and the activation function used in every layer. If we have this information, we know how we are going to do the training process. So the model hyperparameters are set. Okay. The next thing that we need to set is basically the weights and the biases. Okay. So these model architecture, this needs to be fixed before training starts. The other hyperparameters, they specify the details of the training process. And that basically includes things like the learning rate and the optimizer used. Okay. So with that being said, you already know what kind of optimizers are available. We have already discussed this. Some of these include the stochastic gradient descent method. So these include stochastic gradient descent, which is SGD, and its variants such as ADAM, which is adaptive moment estimation, or SGD with momentum, and RMS prop, root mean squared propagation, etc. Okay. So with this the model architecture and the training process would have been fully specified. Now if you have to optimize the hyperparameters, so optimization of the hyperparameters, as you know, is typically done with either using a simple validation set or a single validation set. Because training of neural networks is very expensive, cross validation is difficult. So either you work with a single validation set, or if you are willing to set forth the compute time, then you can also do cross validation. Okay. But mostly people like to work with a single validation set by monitoring the train loss as well as the validation loss. Alright. So, this is all about the hyperparameters and how we will choose them. Okay. So, now we come to the actual training process. So, how does the training occur for a neural network? That is the question we are trying to answer, and we will try to go step by step. So, the first step here, right, is you actually have to compute the loss function, and this involves something known as forward propagation. Or forward pass. Okay. So, this involves propagating the feature values through the neural network to predict the target variable for each point in the mini batch of the training set that is considered. So, in the mini batch of the training set that is considered. Now, why are we talking about a mini batch? Because as we already discussed, training of neural networks is an expensive process computationally. So, for this reason we use a stochastic gradient descent method or its variants such as ADAM, SGD with momentum or RMS prop, and in this process you divide your training set into batches, right, mini batches, and thus whenever you want to update the parameters you only have to compute the value of the target variable for each point in the current mini batch. So, that is what I am writing here. Okay. And of course, what this will involve is that your data has to propagate through the network. So, in this process the feature values are transmitted from the input through the hidden layers to the output layer. Okay. So, this is how you get all the target variable values. Okay. And let us say, as we already considered, that there are n points in the data set. So, now you are having a mini batch, right. Let us say there are b batches. So, if there are n data points and b batches, then each batch will have n divided by b data points. Okay. So, it is this number of data points for which you are computing the prediction, right. So, let us say you tabulate all the data. So, you have features, data point, and then the target variable prediction. So, this let us denote as yi hat. The features already you know is a feature vector for the ith data point, and you will have to do it for all the data points in your current mini batch. Okay. So, this whole table will have to be filled out, you will have the feature vector and you will have the target variable prediction, and this is done for each point in the current mini batch. Once this is done, obviously you can compute the loss function. So, the second step in the training process is the loss function computation. So, once you have done a forward pass for each data point in the mini batch or a forward propagation through every point in the mini batch, you will have the target variable prediction for every data point, and of course you also have the true values, right, available with you for every data point, and from this true value you can compute the loss function. Okay. So, using the values yi hat computed from the forward propagation procedure, we compute the loss function, the appropriate loss function. And at this point I just want to remind you that there are so many different loss functions. Hopefully by this point in the course you know all these different loss functions. So, you can have the root mean squared error, you could have the mean absolute error, this is the L1 loss, this is the L2 loss, sorry, this is the L2 loss and this is the L1 loss. You can also have, if you are working on a classification problem, the cross entropy loss. So, either that can be a binary cross entropy loss if you are working on a binary classification problem, or a multi-class cross entropy for a multi-class classification problem, and so on and so forth. So, there are so many other loss functions. We discussed the 3D loss function, the mean absolute percentage error, and so on and so forth. So, I hope you remember the expressions for all these loss functions. If you do not, it will be a good time to look those up again. Alright. So, now that you have computed the value of the loss function, which is L, the next step is to actually do something known as back propagation, wherein you will compute the gradients of the loss function versus all the parameters, and then you will update those parameters as we always do in a gradient descent based method. So, the third step is called back propagation, or known in short as back prop. So, in back propagation we use the chain rule from calculus, and it will become apparent in a minute why we have to use the chain rule here. So, we will use the chain rule in calculus to calculate the gradient of the loss function denoted by L with respect to every bias and every weight in the ANN, right. And the reason for doing this is of course obvious, because these weights and biases, these together form the model parameters. The weights and biases together, they form the model parameters. Okay. Once you have done this, the back propagation step, you get all the gradients, then you can easily do a parameter update, right. So, that is the next step, parameter update, and here the chosen optimizer whether it is SGD, with or without momentum, Adam, RMS prop, etc., is used to update the model parameters. Okay, which are basically the weights and biases. Okay, and typically you know that this kind of an update, I am just writing it for the weights, is of this particular form. So, the W in the previous iteration is replaced by W minus gamma times del L del W, this is for one of the weights, and of course there are many variants. This I am only showing the basic gradient descent equation. If you go to these other methods like Adam, RMS prop, you will have to change these equations where you have some kind of adaptiveness in the learning rate. So, this gamma, if you remember, this is the learning rate, and this del L del omega is the gradient of the loss function versus the particular weight with respect to W computed via back propagation. Okay. So, back prop is essential, without back prop you will not have the gradient of the loss function and you would not be able to update the model parameters. Okay. So, I hope this makes sense, and of course as you know in any kind of an iterative method you have to continuously keep on doing this, you have to repeat steps till you have the desired value of the loss function, till desired model performance is reached. Okay. So, like I said, this is where you typically monitor both the train and the validation loss, because you are not really doing a cross validation process. So, the train and validation losses are monitored versus the number of epochs elapsed, right. We have come across this bird in the past. So, what is an epoch, right, because training of ANNs occurs in mini batches, right. You know that training data is divided into random batches, and an epoch refers to a full pass over the training data set. So, an epoch refers to a full pass over the entire data set, that is every batch has had a chance to update the model parameters. Okay. Right. So, just to recall that training data is randomly divided into batches of roughly equal size. So, as you can imagine, the number of batches is also a hyperparameter. that will affect the training process, and because the data is assigned to these B batches randomly, that is where the name stochastic gradient descent comes from. The stochasticity is coming from how the data is randomly divided into batches of roughly equal size. Okay. And you also should recall that each iteration of the optimizer, each optimizer iteration employs one batch, right. So, the gradients and the loss function values computed from one batch. Okay. So, if you now plot the loss function versus the number of epochs. So, on the vertical axis I am plotting the loss function or just the loss, or some people like to call it the cost function, versus the number of epochs. Okay. What you will see is typically your training loss of course will fall, keep on falling. So, this is the training loss, but if you look at the validation loss, right, the validation loss will also keep on reducing, but it may not reduce as much as the training loss. So, this is the validation loss. Of course, the plots I am drawing here, they are only representative, they may or may not represent what happens in your case, right. So, you should monitor the train and the validation loss to prevent overfitting, right. So, monitoring both losses helps prevent under and overfitting of the ANN, right. You already know that if your training loss is too low, but the validation loss is high, that means you have overfit, and if the training loss itself is high, then you have underfit the model. Okay. So, the procedure is stopped when the desired value of the loss function is reached. Right, which is basically the model performance is reached. Okay. So, now let us go ahead and see how we can apply this to the example network that we had considered. If you recall, we had an example ANN which we have been considering for the past few lectures, and this, right, please look up the notes from the previous lectures. So, you will have to look up the notes from the previous lecture, and you will remember that we considered a node with ANN with 3 layers. One was of course the input layer with 4 nodes or 4 features, then we had one hidden layer with 5 nodes, and then we had an output layer with just one node, right. We were only trying to predict one value. So, we had one node. It is possible to predict multiple values from an artificial neural network. Okay. So, these were the 3 layers, the first layer, the second layer and the third layer, and if you also recall, no activation was used in the last layer, in the output layer, right, as this network was for was for regression, right. If you are doing classification, then the output layer typically should have a sigmoid, because that sigmoid activation or the logistic function will give you a value between 0 and 1. If you are doing multi-class classification, then the output layer should have a softmax activation, but when you are doing regression, you do not want an activation function in the output layer, because that is how you can get the most unrestricted form of output. There are no restrictions in terms of the numbers lying between 0 and 1 or summing to 1 and so on and so forth, right. However, of course, activation functions were employed in the first two layers. Okay. Now, if you go back and look up your notes, you will see that the equation of the final prediction y hat as a function of the feature vector, right, can be written as B1 2, the bias that feeds from the second layer to the third layer, plus some j equals 1 to 5, because there are 5 nodes in the hidden layer, times W1j. So, the node the weight for the jth node in the second layer as it feeds to the first node in the next layer, times the activated input, right, of Bj1. So, the weight for the jth node as it feeds to the next layer, right, plus some j dash equals 1 to 4, because there were only 4 features in the model, Wj j dash, right, weight of the j dashth node in the first layer as it feeds to the jth node in the next layer, times the feature value xj dash. Okay. So, this is the model prediction, and as you can see, we have not applied an activation function in the second layer, in the last layer, and presumably that is because we are using this for a regression problem. The other thing you will already recall is the number of parameters in the model. In this model, and we had calculated this last time. So, there were 6 biases and 25 weights. You can again go up and check your notes, but you will see this calculation was explained in detail last time, and therefore, there are 31 parameters in the model, right. For now, we have already specified the model architecture. So, that is good, the hyperparameters are already known. What is now required is we need to go ahead and set these model parameters. So, let us say we use the sum of squares loss function. So, this is, for example, we employ the sum of squared errors SSE loss function. So, now you already know the expression for the loss function. So, L, and this is defined here as the SSE loss function, which is one of the most favored loss functions for a regression problem, and you know that this is simply sum I going from 1 to n. Here, of course, I am writing it as n. I am assuming that we are only using one batch in the training process. So, that is why all the training data is included here. So, the difference between the predicted value and the true value whole square. Okay. So, this can be written as sum I going from 1 to n yi minus, right, this whole big expression. Okay. So, let us write that here, that is basically B12 plus sum j going from 1 to 5 W1j to g of Bj1 plus sum j dash going from 1 to 4 Wj j dash of 1 times xj dash whole square. Okay. So, this is basically the loss function, okay. And if you remember, this can be written in a convenient way as ZG2 because it is the pre-activation value of the jth node in the second layer, okay. Now, if we want to apply the gradient descent method, right, then we need to know the gradient of the loss function with respect to every bias and every weight. So, let us try to evaluate some of these gradients, which is basically a partial derivative, right. So, we need the partial derivative of the loss function versus the model parameters, and initially I will compute the derivatives with respect to Bj1, right. So, this means this is the bias, right, of the nodes as they feed into the second layer, the jth node in the second layer, okay. So, this is can be computed as some I going from 1 to n. You know that differentiation can be taken inside the summation. So, the summation will come out some I going from 1 to n, and then you have to basically differentiate this whole big expression, which is some I going from 1 to n yi minus f of xi vector whole square. Now, it is at this point in back propagation. So, this whole process when we are computing the derivative, this is basically back propagation. Back prop, since we will have to work backward, right, from the last layer to the first layer. So, that is why this is called back propagation, and here inevitably we will have to use the chain rule, because if you see you have yi minus f of x whole squared. So, if you want to differentiate this, you will first have to differentiate whatever is inside, right. You will have to differentiate this whole function with respect to what is inside, and then you will have to differentiate what is inside with respect to the independent variable there, and keep on continuing this. So, the derivative of this whole function with respect to what is inside that is basically 2 times yi minus f of xi times the derivative of yi minus f of xi with respect to del bj1, okay. So, this essentially is from chain rule. So, you will have to look up the chain rule if you do not remember it, but that is really important. So, this becomes some I going from 1 to n twice of yi minus f of xi times, you know that yi is a constant. So, the derivative of a constant, right, is 0. So, what remains is simply minus del f of xi by del bj1, right. So, the weight of the jth node in the second layer, that is the bias of the jth node in the second layer, that is what we are looking at. Alright. So, what happens next? What happens next is we will have to find the derivative of del f by del bj1, and you know that f is basically this whole expression here. So, you have to differentiate this cumbersome expression with respect to bj1, alright. So, then what comes now is you will have some I going from 1 to n twice of yi minus f of xi, okay, and then you also of course have the minus here which I am bringing to the front, and del f del bj1, okay. So, del bj1 is appearing only here. So, you have to differentiate this whole f with respect to that. So, when you go term by term, the first term here of course will not contribute anything, right. So, this term will not contribute anything when you are taking the derivative with respect to bj1, and then you will come to this summation, and even in that summation only one term will contribute which actually has that bj1, right, because we are now taking derivative with respect to a specific j, right. So, j has to be either 1 or 2 or 3 or 4 or 5, you are taking a derivative with respect to that specific bj. So, the summation will disappear, this will also disappear, what would just remain is w1j2, and then you will have to take the derivative of what remains. So, that is g dash, right. So, primes are used to represent derivatives. So, g dash zj2 now times the derivative of zj2 versus bj1, okay, and that you can see from here this term will not contribute. So, this is essentially just 1. Okay. So, finally, we have managed to show through this back propagation, right, you are propagating from the back of the network, right, all through the front. So, then this is del bj1 is equal to some I going from 1 to n. Remember, we are considering just one batch here. So, that is why we have all the points, and then we have minus 2 yi minus fxi w1j2 times g dash zj2. Okay. So, this is one example of back propagation that I have taught. I want you to check, right, this is an exercise for you, that del L del w j j dash 1, right, these were the other sets of parameters. You can check that when you write the chain rule back propagation for this step, you will get some I going from 1 to n minus 2 yi minus f of xi. So, this remains the same times w1j superscript 2 times g dash zj2, all that will remain, but you will also get xj dash, the feature. Okay. So, please check this, I hope you will be able to do it. Okay. So, now we are almost at the end. So, this is back propagation. So, why is this called back propagation? So, this procedure is called back propagation since the residual at each point this term, right, this is basically the residual, the difference between the actual and the predicted value. So, the residual at each point is propagated backwards to determine the derivative of the loss function. To be more precise, you should say the partial derivative of the loss function with respect to various model parameters. By the repeated application of chain rule. So, this brings me to the end of this particular lecture. In this lecture, we went through the details of the training of artificial neural networks. Specifically, we looked at the various stages. First, you actually have to compute the value of the loss function, and for that you need the prediction of the neural network. So, you do get that through forward pass or forward propagation, and once you have the value of the loss function, you can then of course, you will have to apply the appropriate loss function MSE, SSE, MAE or cross entropy loss, and then you will have to use back propagation to obtain the derivatives of the loss function with respect to each of the model parameters by the repeated application of chain rule, and once you have the gradient, basically you can apply the gradient descent method and then keep on doing it till the desired model performance is obtained. In the next class we will get into some more subtleties of the training procedure and try to mitigate some of the challenges that arise when we try to train complex and deep neural networks. Thank you for joining today, and I look forward to seeing you next time.